see if I'm live on any of these things. Oh, looks like I am. Cool. So I'm live. That. Oops. If I'm live on Twitter, I need to go to broadcast. Solving daily question. I mean, yeah, I guess anyone here. I guess you could hold on for a second while we wait for people to join anyways. Solving daily question, category, source, DeepML. Anyone can chat. Create broadcast. Cool. So that should be up. Twitch. Let's see. Okay. So I guess my only question is Twitch up. Oh, looks like it. Okay, looks like it. Shut this down. Assuming everyone could hear me well. Sorry for all the. I'm just getting used to all this. There we go. Okay. So I think we're streaming pretty well. I have an eye on, I guess, the chat on Twitch and YouTube. X, I feel like no one ever comments on the chat anyway, so probably just gonna leave that be. I wonder what the YouTube channel's even. I don't know, whatever. So today we're going to go through daily question, just try and solve that. I haven't solved this one. Okay, this one's one of our more interesting questions. Also, side note, for people that are following my quest to, for my quest to have Excalidraw, but with, where is it? Apparently you could encode web things. It can code things into Excalidraw, but I don't think Marimo actually encodes into it just yet. Like, it needs to be approved. So I made my own little fork. But now I could create code, and I could create poorly drawn diagrams. And I don't know. I don't know if anyone else finds this useful. But to me, this is like, I don't know. It made my day getting this done, because now I could write, I could just interact with this. Sometimes I could interact with this, and I could also, so theoretically, I mean, I don't need to. I could also grab this. I guess let me know if people would find, like, I don't know if I want to spend time, I don't know if I want to spend time implementing into DeepML unless people think it would be useful, so let me know. Make sure everything's still running. Let me just see. Sorry, guys. Okay, so today we're going to solve the daily question, which is finding Captain Redbeard's hidden treasure. This is a calculus question. It basically, I just think once you take the derivative, I don't know, I'll read it and see. what people say, or what it actually says, because I don't remember it. Okay. Captain Redbeard, the most dangerous pirate in the Seven Seas. Sure, has encoded a mystery ancient map. Instead of an island, it shows a strange wavy curve. The treasure lies at the lowest point on the land. Watch out for these tricky local minimums. The land's height at the point of... Okay. Right. The land's height. Given your mission implement. Okay, so I guess we're given something like, we have a sort of map, and we're given, control and do that, smaller one. We're given something like this. X marks the treasure, whatever. So X is on the bottom, and we need to find our way down there. If I could just, so just, I don't know. So yeah, I guess graphically it looks like this. Let me zoom out a little. So it has a local minimum, so I guess that's the tricky part, so it doesn't get caught here. If I could just grab this. So we have this. I'll keep that there at some point. A Python function that finds the value of x, f of x, which is the minimum, so from a random initialization point. So let's create our little function here. F of x. Let's see. But I don't know if I finished this thought process. It's hard to remember things I spoke about or didn't speak about. But yeah, I feel like this is just fun for me. Let me know if people would find this helpful on the website, like have a little notepad, because currently we just have notebooks, which I feel like are useful. I prefer this just because I could also draw little stupid diagrams. But let us know let me know if you think it would be useful to add, because then we could spend a little time just implementing it in. Shouldn't be so difficult, but everything takes time. What does this function do? It's x to the 4 plus 3x squared plus 2 turn this. Okay, and if I take f of 5, 720, and I'm looking for the global minimum. I mean, I guess we could do this with traditional calculus and find the minimum point. Taking the derivative, second derivative, take the derivative, set it equal to 0, take the second derivative, and what is it, set it equal to 0 and see if it's greater or less than 0. But yeah, I don't know. I could look it up again. I forgot the exact process, which is kind of sad. But I think we're going to go with more of a gradient descent method just to, because I feel like that's more fun. Let me see what the starter code looks like. So we're given the start of x, it's given some initialization, and I guess yeah, okay. So given a random point of x. Yeah, fine. Where's the... Yeah, so probably gonna do something like this. Yeah. So back to this. So where's my mouse? Sometimes I feel like I mess things up on this. What? Oh, can I not? Is it? No, it's not getting confused. That's weird. Let's see. So I don't want to. So we want to find x min. So we will take x equals x minus, called some learning rate, times the derivative of x. So let's go x this. Yeah, I think that should work. And the derivative of x to the fourth, 3x to the third plus 2 is 4x minus, so 4x to the third. 4x to the third minus 9x squared. And you basically take the thing up here, you move it down here, subtract that by 1. Pretty basic calculus. Let's do another one of these, def f d, derivative of f, x, and we will return 4 times x to the power of 3 plus 9 times x to the power of 2. So we have the function of f and we have the derivative of x. So if I'm given a value, make sure I'm doing this correct. It's what? It's x old minus learning rate times derivative. Yeah, okay, I was doing this right. No, I doubted myself. Let's see. So f old minus f squared d of it's f old minus the derivative of f old times the learning rate. So let's say 0.01 times this. If I run this, so that would be x underscore new. And let's say do this for I in range 20, let's say. So this will be run 20 times. But we want, I guess we need x underscore old to be equal to, well, not 0. So let's go f of 5. So that's x old. So we will have let's go x start equals 5. This would be x underscore. It should be x old. Just old. Old. And this would also be old. And then we get x new. And let's make old equal to x underscore new. And we run this a few times. And then it gets upset at me, just as I planned. What did I do wrong? Miracle is out of range. What line are you complaining about? Okay, I'm assuming it's not line 141. Line 4. What did I do wrong? Let's see, f old. So that would be this one. Let me just make sure this works. Let me see why this wouldn't. Okay, I know. F of 5. Yeah, that works fine. Celebrate the numerical result out of range. Okay, let's do 2. 2 worked. Let's see. Old. Okay, so this is just exploding. Yeah, so this is just exploding again and again. So that's not good. So f old. Yeah, right. Through. Oh. I was making a mistake. It's not. It's this. So if I run this 20 times, it's okay. So we think this is our solution right now, but let's see if it actually works. We'll grab it here. It'd be pretty cool if we could also have, maybe I'll do this too, have a little screen of just a DeepML site there. But I feel like it'd be cooler if we have the reverse. Let's see. Start x, whatever, let's do. Old equals start underscore x. And we will return, well, I guess we should turn, I mean, it doesn't really matter, x. I was thinking between x new or old. But I think, if I'm not mistaken, everything's on, oh. Where am I? I need this. Let's go with this. And we also need the other function we made. There. And they're still angry at me. This is what makes this question not great. It tells you the answer there. Yeah, should make a better version of this question. So what is it? Let's take an example. Let me just take this whole function that we have. And let's throw it in here. And then you always have to be angry at me. I know, wait, what do you fine. No, we already have these. We're working on there's a lot of cool things, but did I freeze on YouTube? I don't think so. No. See if anyone commented on Twitter. I'm assuming not, but worth checking. I really don't think it works. Yeah, live chat never. Oh, 3x cubed. Oh yeah, someone actually commented on X. I probably should watch my X feed now. I've never had someone comment on X before, so thank you for commenting. Did I do something wrong, I guess is my question. So they said 3x cubed. Did I not do that? Nope, not frozen. Coolsies. Let's see. Old start 3x cubed. Oh, okay, yeah. Thank you for that. Let me replace that here. Whenever I'm watching someone else's stream, I'm like, oh, how could they make such a silly mistake? And then I feel like I stream and I'm like, oh, I still got it wrong. But let me, yeah, I don't even like these test cases. Oh, let's try get a hint. Let's see if it gives me an actual helpful hint or not. Check your derivative calculation. Four x to the third. Did I not do that? 4x to the third minus 9x squared. But you implemented, that was pretty helpful. Wow, whoever created that feature is a very smart person. Still got the question wrong. But I'm assuming it's closer. Let me copy this over. Whoever made that genius feature, wow. Oh my goodness. I am just complimenting myself. Sometimes does it break? Yes, but it usually works. Let me just get rid of all this. And start from here. Okay, so this is our current code. We know it sort of works, but let's actually see. Let's take a test example that, let's see the one we passed. Yeah, I mean I could just return 2.5 and get the answer correct, but there's no fun in that. But theoretically I should make this question a little better. Let's see. I don't want this. I want find treasure. Let's see. Never closed. Fine. Okay, so that was 2.25 for blah blah blah, and that was correct. But which one did we get wrong? When we started, so quick explanation. I guess it's a test at different starting points. So sometimes we'll start here, sometimes we'll start here, sometimes we'll start here, sometimes we'll start here. And it wants to make sure, you know, you're still finding the treasure no matter where the pirate guy started. Redbeard. Let's see. Find treasure, but I'm assuming what's happening. Yeah, this one starts at 1. And 1, if we look at the graph, is here. I wonder if it's just we're getting caught up with too slow of a learning rate, or let's say run this for 100 iterations, and we'll increase the learning rate a little. Because maybe it's just not, it's getting close, but not close enough. Okay. Yeah, so now we got test case 2 and 3 correct. Here we start at where was that? So I guess before we were starting at 1. Now we're starting at -1. It's like here-ish. And we're probably going down, 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 and then we're probably getting stuck here. So in order to get out of this, we probably should use something like either momentum. Yeah, probably momentum. We could try a little more intense learning rate, and that might skip over it, but it also might just start exploding. Or it might start bouncing around. So what I mean by bouncing around is it could get here and then go here and like just bounce back and forth here and there forever. Yeah, it sort of broke everything. I could keep playing around with this, but I feel like that's less fun than trying to do momentum. Let me see if, because we have problem breakdowns, I wonder what's the, let's see, does it actually say to use breakdown? No, just, okay. It just, I mean, you could also do this question just with calculus and just solve it. But this works. But I think we have a question for momentum. And that could be a fun way of solving this instead of just solving it. Solve 2 questions. Oh, optimizer, nice. Okay, so we're solving 2 questions. Let's see. If moment, let me plug in my computer. Oof. Let's see. If momentum optimization. Okay, so giving a parameter, grad, and velocity. And we output what? Parameters and velocity? Let's see. Let me zoom in. Momentum optimizer. An example. I like examples. Fine. Let's read this actually. Momentum is a popular optimization technique. Yeah. Determine the direction of the updates. So basically we have, instead of, hold on. We have our values here. Instead of subtraction, I mean, I guess usually we just do this. This is what we usually do. This is the learning rate, and this is the Jacobian, whatever. It's the derivative of j of 0, of j of theta. So we're basically adding this term to it. And this term is gamma, the momentum coefficient, yeah, fine, typically 0.9, times vt minus 1. What do we initialize vt as? Computer keeps going dark and light. I don't know if it's an issue for you guys. So let's see. So we're given some parameters, some grad, some velocity, some learning rate, some momentum. And what we need to do, let's see. I think it should just be one output. I don't like when it's a tuple output, but whatever, is what it is. So we have Vt equals gamma. Let me just read this quickly. Let's see, current velocity. Okay, so we have the current velocity Vt. We have, do we not have, I guess the momentum parameter, using that, equals, I just need to add that, just quick, just press tab, momentum times, what was it, velocity. Probably should try to understand things beyond high level stuff, like why does this actually work? I feel like, yeah, it's an issue I feel like I'm constantly having because I keep rushing through stuff like, oh, I need to solve it, and should just enjoy the process a little. So let's see. Let's try and understand momentum a little bit. I mean, I understand it. Yeah, let's try to understand it a little. Let's have some fun. I don't know. I mean, I'm not in the biggest rush. I don't know if you guys are, but I mean, I feel like me solving the questions is probably not. I mean, it's not too useful to me. Like I could write this and write that, and it helps out a little. But understanding is a little more fun. Zooming in and moving things around also seems to be an issue. Let's highlight this. And let's throw it here. Okay. So we're basically taking, I want to just run this to see, like, it doesn't matter, like, I think it said something about velocity on this side as well. Current velocity, Initialize velocity. Okay, initialize velocity at 0. Okay, so theoretically, we have 0 times this, so we start out with just the regular thing, and let's say, for example, this is, there's a big change. So let's say the derivative is high, meaning, let's say we're here, and we take, I mean, gradient descent, how it works is, we're trying to take a step towards our objective. And the intensity of the step determined by, I guess, this factor right here. But, okay, so let's just work out a small example. So the 0 example, this would be 0, and it would just be a single step. And it would be the same thing as gradient descent. So step 1 is just gradient descent. Step 2, that's where it gets interesting. So this equals, I guess, this value right here. Let's just throw in some numbers, but I feel like I'm going to try to not throw numbers for like 20, 30, not 20, like, say 10 minutes. Get frustrated, and then throw in some numbers, but we have to go through the process of, even though probably would be better if I didn't do that, but we will continue on the process. So 2, we would have this value would be the first version of this would be this. Yeah, fine. But this time we will use this. We'll have code. We use sort of like a calculator, and I'm happy with it. Let's use our, I guess, function because we already have all that information. So let's see if I can take this. Restart. Let's do 3 of these, and we'll print old after each one. And we'll start at 3. Okay, so okay, we're getting closer and closer. So theoretically what we do is for each iteration, so this value probably should hold on to, let's say it's the m factor. Should I do 1 letters? No, but I'm doing 1 letters. And we also will have gamma times old v. And then this is plus. I'm pretty sure it's plus, yeah. This learning rate, I mean, I should have things in variables, and this should be meter code, but I'm lazy. Gamma 0.9, they say 0.9, okay. And then old v, so it started at 0. Let's see what, let's also print m. I also want grad. I want to have this separately so I could really see how it goes. Okay, so print old, let's print m. So I have the momentum, and we'll have the grad. Okay, so first, it's the same. Why is it always the same? Is old v, oh, I'm not updating old v? No, I'm not updating old v, so that could do it. Old underscore v equals, what's old v equal? Oop. Old v is the current, I guess that's our momentum feature, right? Yeah. Old v equals m. Okay, there we go. So, grad, we're not doing anything. Okay, so this would be the theoretical grad, so each time. Let's look at our thing to understand it. So we're at 3. so that's around 10. All right, we're starting, where are we starting actually? New, old, yeah, we're starting at 3. So each step, go from, we take 0.27, 0.38, 0.43, so we're taking pretty fast steps down. See what the momentum does. So first, it's just the same thing. I mean, it does nothing. Next, it would theoretically add 0.14 to it. So it's saying, I guess you could speed up a little more. But it'd be more interesting to do this from -1 to, because theoretically that's the issue we're having. Like now it's just going to go down faster. But this is the problem we were having. So we were here, minus, yeah. So, let's see. It should be -n now. Let's print this, and we'll also print the old. Okay. So, I like this a little better. So we're here. Okay, so we're trying to find the lowest value of x. So theoretically, we started at -1, we went down 0.13, got to 0.87. Oh, but now this score's a little messed up. No, it's not. Is it? Okay. So we're here-ish. We take our next step. We get to -0.65. So we're like here. We keep on going down. Next step, we're at -0.4. Let's increase this so we. Let's go 20. Let's see where we end up. So we keep on doing that process and keep on going step, step, step. But I want to see where we hit. I want to see when we hit. Is it going to go past? Yeah, so when does it hit? What is this, like 0.5? So at some point, it'll hit 0.4, 0.5. And I'd imagine the gradient shouldn't move much, but I guess we have the momentum feature, which would move it a little bit more. Let's see. Let's see. So we have the momentum feature, which basically looks at our last step and says, okay, so it's saying like if it suddenly drops down, we're still looking at the last feature as well. So if we just came off, okay, momentum makes more sense. If you just came off of a strong decline, it would, hold on. What's that? Sorry about that. Let me. Timer. Helping my wife cook something. I mean, she needs. I mean, not really helping her cook anything. She's cooking something, and she wants me to take it off the fire because she might not be able to. Yeah, sorry about that. Okay, so yeah, I guess the momentum makes sense because if theoretically, if our last step was very strong, we would basically add a little bit extra to it. So instead of like, right now we would have nothing, but we look a little back, and instead of having a 0 gradient, it would actually continue moving past some, not all, but some local minimums. So we could find our way to the lowest point where the actual treasure is in this example. Okay, I'm gonna. Yeah. I don't really want to solve this one. I want to solve the daily question first. Maybe I'll come back to it. Oh, thanks for joining. Let's see. This one has 4. I'll check out the comments after I solve this. So let's see if I actually remember this. So we have v equals 0, let's say, and v would be 0.9, which makes this a variable, but whatever, times grad. So let me take grad. Let me put this at 0.01 also. Grad equals this. 0.9 times grad. So that would be our old gradient plus the learning rate time. Oh. Hold on, am I doing this wrong? Does it matter? That was another question. So this would be the first gradient. No. Okay, this is wrong. I mean, this is right, but we'd have v starts out at 0, so this would be times v plus grad. Grad will do here. And this will be minus v, or m. Darn it. Whatever. Let's see. So we will do what was I thinking? Minus v, which is velocity, so but the next time velocity will be this, which I don't know if that's correct. We want, oh, I guess we do, yeah. Okay. This is correct, I think. Let's run this and see what we get. Oh, nice. Oh, cool. We solved it. Let's say this was a fun question. I mean, yes, you could just cheat the whole thing. Let's see what the comments say. You could just cheat the whole thing and you could just say 2.25 and you get your correct answer, but I feel like it's a fun question. Let's see what the comments say. It's not printing anything. I don't know if it's true. The solution can be solved. Even lower the learning rate increases the number of iterations. Doesn't help. Yeah, this is true. Yeah, this is correct. Oh, yeah, I like this. Nice. Yeah, we need to do it with momentum. Yeah. Let's see. I mean, yeah, I feel like the solution tab shouldn't give you this full solution. I don't see the point of that. Yeah, I mean, I don't know. Should I update the solution or should I give it people? I'll give people an incomplete solution. It's a little rude, but I feel like I don't know. It's enough of a hint to figure out the rest, and it's not the hardest question. I think you guys could figure it out. If you get stuck, you could use the hint feature. Let's continue. Let's see. Just return. I mean, yes, you can just return that and you'll get the answer correct. Yes, you don't need to iterate anything. I think someone shared it above. Okay. Anyone have any other questions I should try to work on? Let's see. Check X also. Okay. I'm assuming no currently, but let's see. That didn't take so long. That was a nice question. Is the lab still down? Yeah. For people that didn't see, I mean, this is my local host, but we have Jupyter notebooks within Excalidraw, so I could draw stuff, and I could run some code. I am enjoying it. I feel like it's a fun way to do things. I don't know. I feel like I should try to do another question quick. I know, this should hopefully be back. And today, hopefully. Because right now we're... Where is it? We're basing... Yeah. We're getting the data sets for our lab from here. And that, I mean, we need a better process. I mean, it's not a good process right now, but it works. And I feel like it's a good test of the idea, see if people actually enjoy it. If people don't enjoy it, then probably work more on regular problems. If people do, we'll probably make more actual problems. I mean, more lab questions. For people who don't know, the lab questions are more practical. It's more like, I think they're pretty useful, especially if you're trying to learn PyTorch or really understand something. Oh. I need to go check on the cooking or turn off the fire. I'll be back in like, I don't know, 5 minutes. Let me finish this now. Okay, and I'm back. Yeah, if anyone thinks this would be useful in DeepML, let me know. Even though I said this 5 times, I might do it anyways because I find it really cool and helpful. I don't know exactly how I'd implement it into questions, but I feel like it would be cool. Random question. Do we try for this? I have another like probably 20 minutes. We could random question it. I probably should make it to the random question. Doesn't give you pre-solved questions already solved. And if I go unsolved and then random. Oh, another optimizer. Which you probably could also use for solving the question. We'll get started. I don't know if we're going to finish this question, but we'll start on it. There's been a single update step for RSM prop. I feel like it's usually used for regression tasks, or maybe I'm making that up, but we'll see. Given current parameter values, gradients, and cache, which stores the moving average of the past square gradients. So pretty similar to momentum. Compute the updated parameter values. Cache, rising crop adapts to the learning rates for each parameter individually by dividing by the square root of the cache values, which helps parameters. I don't think this gives away too much. Gives away a little, but this sort of gives away a nice amount. If you read this, you probably figure it out. Let's have some fun with it. I don't think I'm going to solve it right now. I think I'm just going to study it, try to understand it a bit better. Maybe I'll solve it, but we'll see. I feel like sometimes I get too caught up in solving and not enough in the process, because the process is pretty fun. Let's see. Okay. So it also goes nicely. Happy this was the random question we got. Goes nicely with our theme of optimization. I did have a learning rate optimizer algorithm that adjusts the learning rate for each parameter based on its history of its gradients. So usually we were setting our learning rate, so even with basic gradient, usually we're just setting it, that n, I don't know the actual Greek name for it. We're setting the learning rate. Okay, Jeffrey Hilton, core problem. So this is regular gradient descent. Let's see. Standard gradient descent uses fixed learning rates. So yeah, usually, to explain the problem. I'm happy this is down. We have our gradient descent game. Basically, because labs are down, you can play this game. But it's actually very helpful for our use case. So let's say I have a constant learning rate of 0.5, and our goal is to get here. I'm never actually going to be able to get to the lowest point because my learning rate's too high and I'm jumping around too much. But if I was able to adjust it, I was able to. Still didn't make it in. Maybe I'm not so good at this game. Oh no. I don't think you're able to. Darn it. I guess I got in a starting position where you couldn't get to the actual minimum. Refresh page. Let's play again, but let's assume that didn't happen. So theoretically, I could, if I'm able to shift around my learning rate, I can get to the actual minimum. But then you're like, okay, but let's say I just always started with 0.1. This way, I'll take steps and I will eventually get to it. I mean, you're right, but I'm going to waste so much time. I mean, here it was 8 steps. But if it's an actual problem, you're gonna waste so much time, and your model's not gonna really learn anything. So, darn it. RMS. So you wouldn't actually solve it if the learning rate's very low. But if you're able to change the learning rate correctly, then you'll actually solve this. Or actually be a lot more efficient algorithm. Some dimensions have steep slopes. Okay, you need small steps, and sometimes you need large steps, like we said before, sort of. Yeah, so where's my... Oh, no. Darn it. There we go. Yeah, I mean, this is... I made some edits to it, so it's not as smooth as regular Excalibur. Let's see. Yeah, so right here you'd probably want, maybe you don't need the biggest learning rate because right, it's going to go down a lot. Like you want it to be able to move and groove with it, but here when you're lower, you probably want a higher learning rate so you don't get stuck at the minimum. So, the RMS prop algorithm. It's also too long. Like the name itself, not the learn section. Okay. So first, we do what's beta decay rate. Same thing as the velocity and the other thing. So we're taking. Okay, so this is more of a weighted average from what's GT, I guess. So this is the old velocity. This will have, let's say it's 0.5 and 0.5, then they're equal if it's 0.9, this would be 0.1, making you'd look a lot towards the last one and not so much towards whatever this whatever G2T is. GT is the current gradient. Why are we squaring it? I guess we'll get there. I square my gradient. Just trying to think what that would actually do. Because, okay, without the squared, then it would just be... I mean, this could be like... Yeah, this is the... What's V? Moving average of the squared gradients. I'm pretty sure this is just what we just did last time. It's the momentum. Okay. And this is basically saying how much do we want to look towards the past and how much do we want to look towards the future. I guess this part is new. This part was just the learning rate. But now it's saying the learning rate. Right. Let's look at momentum again, really quick. Yeah, before we had the learning rate. But now we have 1 minus the decay. Update parameter, cool. Theta minus the learning rate, base learning rate, divided by this element that we just computed, Vt, plus some small epsilon, so we don't divide by 0, just in case, times Gt. So this is, okay, division in the square root, element-wise. Why this works, adaptive learning rate. Okay, I understand. Yeah, each element in the gradient. Okay, fine. Why is this large? Yeah, I guess that's probably. Let's see. I'm gonna try and do it without reading it. Just try and see if I can understand it. So if we had a really big change last time. So we had a really big change last time. So this value was really big, so we had a really big change last time, so we would sort of remember that. Let's say our starting learning rate's very high. We have, I don't know. But are we updating the learning rate, I think? Why is it always just that high? So we just have a base learning rate. Okay. So if the base learning rate is 1, let's say, and we're in the middle of the process, and Vt, this process equals 2. So this is half. So the learning rate would be half. And Vt would move in that way. When would Vt, like, what lowers and higher Vt? Let's get rid of the epsilon just for the ease of understanding. So if this is very high, what does that mean? It means our gradient is very high, and last gradient is very high, whatever. So if we have high gradients, the learning rate, because this is just replacing the learning rate theoretically. It's just replacing the learning rate theoretically, but it's more dynamic. It's basing the learning rate. It's basically saying the higher the momentum, the lower the learning rate. Okay, yeah. So that's pretty much what they're saying here. Because if we have a really high momentum, we don't need such. Okay, again, and that's I feel like what we were saying before. Like, if we're, here and we're going down quickly, we don't really need such a fast learning rate because it's already going to move down a lot. But in examples where we start slowing down, the momentum's not so high, so this value's not so high. We'd probably need a little, we need a little push. We need a little extra. We need the learning rate to be a little higher, or ideally the learning rate would be a little higher. So, like if this is 5, so it's a very high shift. This is just a weighted average from last time's thing. It's probably stuck at 0, because the first iteration of VT, like V of 1, the V of 0 is going to be this. Which is basically whatever, it's this value. I don't understand why you square it right now. Like, I feel like I could not square it and it would have a similar result. Oh, I wish we had the labs open right now. Because there's one question where you implement your own optimizer. So let's say I would want to, let's say I just implement this. But I do it without the square feature and see what happens. See, maybe I'll get better results, maybe I'll get worse. I feel like it's pretty cool. Anyone else have any? I mean, I'm not going to solve this right now, to be honest. But I understand the core concept of it. And I think it's pretty cool. It's a pretty cool idea of just having, I guess, a more dynamic learning rate. Did I miss anything? Oh, I want to know why we square it. Oh, is this what I wanted? What is this? Wasn't? Okay, now I'm a little confused because wasn't this? Hi. The exponential moving average gives more weight to recent gradients while still considering history. But where did we get why do I... Probably should read the rest of it. It seems pretty interesting. I mean, I don't know how we're getting to the second order derivatives. What's the Haish? Where's that word? Haitian matrix. I'm definitely pronouncing that wrong. Yeah, I feel like I'm... The sign of someone that self-studies a lot of things is they don't know how to pronounce things out loud. So you're just reading it in a book or something. I mean, I guess you could be a self-studier that watches videos and then actually know how to pronounce stuff. But if you're reading books, you don't usually know how to pronounce all these things. Like epoch, whatever. And I think it's epoch. Well, that's at least how I say it. Okay. I don't understand what is this? We just said what V was. We defined V already. Why are we redefining V? Gradient normalization, approximation normalization. Okay. Let's see, versus momentum. Yeah, at some point, yeah, I probably should do a optimization journey. just go from regular gradients to eventually to atom, and then what's the new one? Mui is something with an M. Optimization. This one. I think I need to update the collection because I know we have an optimization. Yeah, we have an optimization collection. I finish it with the Captain Redbeard's thing that we started with. That's annoying. That shouldn't go there. That should take me back here at least. Optimization. I should probably switch this order. We shouldn't start with atom. Atom should be lower. And I should also add in the muon, whatever it is. Okay. Thank you guys for joining. Let me know if you have any questions or concerns or I don't know, something breaks. Have a good weekend, everyone.